All right, good morning. My name's Laura Waters, and I'm in the second year of my Buck postdoctoral fellowship in the Department of Mineral Sciences, working with Ben Andrews. And so today I'm going to talk about the origins of volcanic glass and how we can use these origins to resolve obsidian, and it's sort of a paradoxical material. And so why study obsidian? So the first reason is that, for the talk today, is that it's sort of a weird material in nature and it's strange that it should occur, and we figured out why it occurs here at National History Museum. In doing this research, we've also determined how large crystals grow in nature. And by studying the origin of silicic melts, we actually get at some of the processes that go into the formation and origin of continental crust. But today I'm just going to talk about the first two things. So I've mentioned that obsidian is a glass. Here's a picture of a few obsidian hand samples, and a glass is a solid with no repeating molecular arrangement. And so this is weird to sort of find in nature. So what normally happens is that you have a melt, and a melt is a collection of molecules that are continuously breaking and reforming. And so when you subject this melt to cooling or a loss of water, you take energy out of that system, and these molecules arrange themselves into lattices, and we call them crystals. And so what happens with obsidian is different. Now, when you look at chips of obsidian underneath the microscope, what you see is beautiful sea of glass and sparse large crystals. Now, that's kind of weird because when you look at how obsidian erupts, it actually erupts slowly. So some magmas erupt explosively, so fast, there's no time for crystallization, which is one way you get a glass. But obsidians ooze and extrude out of the earth, so that means there's plenty of time for crystallization because they erupt slowly, which is why they're paradoxical. So the obsidian paradox is that obsidians erupt and cool slowly, suggesting there's ample time for extensive crystallization. Yet obsidians consist most of glass. So why do these melts form a glass? And what I want to know is there a process that affects how these melts crystallize? In order to address this, we need to do some experiments to identify conditions where crystallization occurs on Earth, and also recreate these obsidians in the lab. So to do this, we're actually going to make magma here at the Smithsonian. Now, here's what we use. These are experimental vessels, and what you can see is they consist of a furnace that reaches magmatic temperatures and a pressure vessel that can reach magmatic pressures or depth. And using this setup, we can actually reach a range of conditions in the Earth to see where crystallization occurs. So you see here it's 700 degrees C to 900, and then a depth. And just a reminder that in the lab, we can't actually take the samples down to 6 kilometers beneath us, so we're actually controlling the depth by controlling pressure. And just a reminder that for both depth and pressure, 0 is the surface. And so using this setup, we can conduct an array of experiments. So here are experiments as the gold dots, and each gold dot is a gold capsule with a piece of obsidian inside of it. And using that experimental apparatus upstairs, we're going to actually melt this obsidian and see if something grows or if it's just a liquid. So after we finish each experiment, we quench it and we see what grew. So sometimes we find experiments with 100% crystals. Sometimes we find experiments that are 100% liquid and they didn't grow anything. And sometimes we grow liquid and crystals. And so we've got our first result, which is we've actually mapped out space in the Earth over temperature and depths where obsidians crystallize. But that's only part of our project here. So for the obsidians, we actually want to recreate them. So just a reminder, obsidians consist mostly of glass and a few large crystals. And we also know that in nature, they ascend slowly. And so what we want to know is, can we reproduce these natural samples in the lab using slow ascent rates? So we can't do it quickly. We have to do it slow because that's how obsidian erupts. And remember, in the lab, we're controlling depth by controlling pressure. So we conduct a decompression experiment, which is the red line. And we decrease pressure over time in the experiment, which correlates to an ascent rate. And just a reminder, here's what our samples look like. Lots of glass with sparse big crystals. And given the length of the talk, I just want to show you how we did it. So we managed to grow samples that look similar to the natural samples in the lab. And we did it by starting from 100% liquid. And this is important because we didn't have any crystals there or nucleation sites, which means all crystallization happened on the way up. And so here's a picture of what we grew. This is an electron image of the experimental run product. And what you can see is we grew a sea of glass, which is the dark gray, just like our obsidian in nature, and a few big crystals. Now, our samples are in good agreement. The experiments we grew in the lab are in good agreement with the natural samples in terms of crystal size. Our crystals look a little bit different, But I want to show you how good we did by showing you a negative result. So we did another series of experiments where we started from the field of both liquid and crystals. So we were saturated with both crystals and tiny nucleation sites before decompression. And we decompressed, we actually grew lots of little tiny crystals, which is not even close to how the obsidian looks in nature. And so with this negative result, we actually have found that in order for obsidians to erupt and ascend slowly and crystallize sparse large crystals, we actually have to begin as 100% liquid. And so in doing this, we've actually resolved the Obsidian Paradox, which is that obsidians form not by rapid cooling, which is what people commonly say, but because they were 100% liquid and contain no pre-existing crystals prior to ascent. We also, in doing this work, discovered that large crystals can actually grow during ascent and they don't take a lot of time. And then lastly, in the absence of pre-existing crystals, this is actually what inhibits extensive crystallization and results in the formation of volcanic glasses. Thank you. So the question was, would we be able to use crystals in the natural sample in conjunction with our experiments to say something about how quickly obsidian ascended through the earth? And that's a fantastic question. The answer is absolutely yes. The problem is that not all liquids always start from a 100% liquid field. Sometimes you start with crystals, which sort of complicates the kinetics. But that's exactly what the objective of the project would be. Thank you. So why obsidians? Well, in our community, there's no consensus on the processes that go into the origins and formation of continental crust. And so I'm particularly interested in integrating crystallization kinetics into discovering how melts form within the earth. And so obsidians provide a great material to answer that question because, as you saw in the talk, they are kinetic mysteries. Well, they were. And what's nice is that by looking at these and deciding how melts form, we're actually getting at the processes by which silicic melts form and how continental crust is made on Earth, which carries implications for how continental crust could be made on other planets. Yeah. So the question is, how long does it take to replicate crystals in the obsidian? So the second set of experiments, how long are those decompressions? So if you're a runner, you're going to be really excited about this. So these experiments were conducted at, about 1 MPa per hour, which is equivalent to about 60 meters per hour. So for humans, that would be longer than an hour to walk a football field, and as like a slow runner, yes, it makes me feel great. But they're actually quite slow, so you could outrun an obsidian eruption. Yeah.